Okay, so in that 10th question under friction that I gave for homework, it's asking for values of P. P is that external force applied on that particle, not along the slope, but at an angle to the slope. So what answers did you get? Let's see whether our answers tally. Values of P, so it's a range of P, just like from the minimum to the maximum, any value P can take. So you have to find that extreme values, the min and the max. Hatvi says max is 1.04 newtons and min is 0.675 newtons. Is that right? Hatvi, can you put that to the whole, to everyone? Or shall I copy it from you? It's windy today. I need the wind. Oh, okay, Malik, that's what he got as well. So let me put it to everyone. That's not how you should keep the answer. If they're asking for the set of values of P, you have to say 0.675 greater than, 0.675 greater than P smaller than 1.04. Actually, the equal sign should come too. It can be equal to this as well, like that. The range of P, range of values of P. So P, the external force applied on that particle, P, can be in between 0.675 and 1.04. Any value within that range. Miss, will we get questions with tension also asking for values of P? What do you mean? In what kind of a scenario? What do you mean tension? You mean you're applying that external force using a rope or a string? It's the same thing. It doesn't matter how you are applying it. That external force, you could be applying it directly by holding the object and pulling it, or pushing it, whatever, external force, or you can be pulling it with a rope. That doesn't matter. That P could be coming along, applied along a string, in which case it will be called tension. That is still the P. That is still the external force. Is that what you're asking, Hatvi? Okay. So let me say that again. That's a good question, Happy. In these friction questions, when you have kept something on a slope, right? When you have kept something on a slope, when you have kept something on a slope, see the friction on my hand. When you have kept something on a slope, I will make that the background, so then it's clear. Now it is not sliding down because the friction between the eraser and my hand is enough to prevent it's balancing exactly the component of the weight of the eraser downward. If it is like 1 Newton downwards, that is a 1 Newton friction upwards. Now, if it is trying to, it's sliding now, if you can see it's sliding now. So I have to apply an external force. That force can be applied directly. Like I can hold it and apply it, or I can put a thread around it and pull it along the thread. It doesn't matter in what way you exert that force. It's still your external force. Only thing that if you put a string, that force is transmitted through the string, so then we call it tension. But it's still the same. Okay, doesn't change anything. Right. Then I hope everyone got it. If you did not get it, you have to get that answer. So the answer is now given. You have to somehow try and get it. You let me know if you did not get it, because we did enough number of questions for you to be able to handle a friction question on your own now. So I expect you to be able to do it. Okay. If you were not able to do it, then there is a problem. So then you have to let me know. Okay, so we are going to start this topic, connected particles. It's not a separate topic. If you look at the syllabus, it doesn't, it's not listed as a separate topic, but it's a certain kind of problems that can come under Newton's laws, friction. All of these are applied in these questions. So in the textbook, you have a topic dedicated as connected particles, and that's what we are going to address now. In any mechanics paper, you have a connected particles question. Okay, so this is important. It's important because you have to know everything. Now you have to be armed with, equipped with, ready with everything that you have learned so far in mechanics, starting from motion, linear motion in a straight line, all the way up to the last thing that we did, that is friction. Okay, so I have this short note that I have made. It's only 2 pages. This and this is a short note, because there is no new theory. I have given you a strategy in tackling these problems. That's it. That's what you have in this note. So if you haven't taken the print, I'm sorry, I sent it to you in the last moment. I thought about it in the last moment. I thought, why not I send it to you, so then we can save the time that we will be spending to write it down. So what I will do is, you take a printout leisurely, read it later. What I'm going to do now is we are going to straight away start the problems. Okay, so I sent 2 files. One is that short note, and the other one is the worksheet, connected particles worksheet. And if you are wondering what are connected particles, these are connected particles. I will show you all the diagrams in these questions, and I'm sure you also have seen these in past papers. A scenario where you have 2 or more particles connected with a string. These strings have a special property. They are said to be, I'll show you the word, inextensible. In any question, they say that the string is inextensible, which means it doesn't extend. There is no Hooke's law coming into play here. You know that according to Hooke's law, an elastic a material like a rubber band or a string or anything, actually in practical, these rods, or even a rod extends slightly when a force is applied on it. But we assume that these strings do not extend, so that the tension is transmitted as it is along the wire or the string or the rope, whatever you call it, the thread or whatever, right? So, and also they will always say that it is light. It's light and inextensible. Light means we don't think of the weight of the rope, that will be acting on these particles. So all that is ignored. Our system is only the 2 particles. Okay. So this is one example for connected particles. So what are we finding here? Certain things, so if you, for example, if I have this setup, so this is a pulley. So the string is going over a pulley, and at the 2 ends of the string, you have 2 particles, maybe of different masses. And if you release the system, maybe say you are holding it in one level, and if you release it, it will start to move. It will start to accelerate towards a heavier particle. And then we can talk about things. What's the acceleration? How far will this go? With what speed will it hit the ground? What happens after hitting the ground? Things like that. So we will explore all that. Here's another scenario. Again, connected particles. Here, one particle is resting on a plane. Oh, now, wait. Is there anyone here who's joining in via the mobile phone, or are you all on your computers? Anyone joining?
Miss, today I'm in the mobile phone.
I'm in the mobile phone, miss.
Ayo, who? Nathan and Tarindu?
Yes, miss.
Today I'm at home.
Kavindu. Oh, that's not. How do you do that? You are looking
miss, all this time, ever since we had online classes, I only used my mobile phone. I didn't have a laptop. My laptop went kaputski.
Because now when I show you something like this, do you see it on this?
Yes.
You don't?
Then miss, we switch to the thing that you are showing.
Can't hear. What?
We switch to what you are showing. It's either the camera or the screen share.
Can't hear you clearly, Tarindu. What did you say?
Miss, we can, if you could you screen share that, miss? That would be easier then. then we can see
Yeah,
easily.
sure. When we start the questions, I will be screen sharing. But I'm just, for the explanation, I'm showing you like that. No, it's not clear then, right? Even when I screen share, it won't be clear. It's just the mobile screen. Ayo. Okay, so this is a request. Can you please try to get borrow? You can't, it's not, if it's not effective. Okay, we are wasting time talking about it, so I will just carry on. Okay, so this is okay. Let me share the screen. Right, that's another scenario. Just look at the diagrams. We will be doing all these questions. This is another scenario. Connected particles. Two particles are connected with a string, light inextensible string going over a pulley. In this case, one is on a ramp, on a slope, other one is just hanging, and when you release it, what will happen? And we can talk about what things happen, how far they move, and all sorts of things. And as you can see, as I said everything comes into play here. Newton's laws, F equals ma. For the if you want to find the distance traveled, equations of motion will come into play. And then if this slope is has friction will come into play. All of these things that you have learned so far, they are going to be part of these questions. Okay, so if I take you to the next, I'm just showing you the diagram. See, connected particles. I'm just just trying to give you a sense of what connected particles means. It's just a name given to a certain type of problems that you give. It's not a theory. Connected particles theory, there's no such theory. It's not a theoretical topic. Okay, it's a name given to a certain kind of problems that you get in the paper. So here too, you have both particles resting on surfaces. So there will be lot more forces acting on these two particles than in this case when they are just hanging. The only, now if you look at here, if you think of one particle, there are only two forces acting: the weight and the tension. Weight and the tension. That's all, because they are just in air. But if a particle is also on a on a surface, you will have reaction. If there is friction, you have friction. If the surfaces are not smooth, you will have friction, and all of that. So that here both particles are on surfaces. Let's look at number 4. No diagram given. You have to sketch a diagram. Number 5, again, connected particles. One is on a, it's weird positioning. Again, simple scenario. Again, right? So when you see all these diagrams, you get a sense of like, so when you see the diagram, you know this is the connected particles problem. Okay, and all different ways in which you can have the two particles connected, and how they are placed. Are they just hanging in air, or is one of them on a table or on a ramp, or both of them are on a ramp or something like that, right? These are the different scenarios. So I just showed you everything. There are 10 questions here. We are going to do all of them. So let us start. So as I said, in the short note I sent you, I've given you kind of a framework to keep in mind, like a strategy to navigate these problems. But I would be modeling it to you. I would demonstrate that to you by actually doing a problem. Okay, then later you can, when you read this, it will click to you. So that's why she did it that way, or something like that. Okay, right. So let us look at this first question. So you write your topic, connected particles. Today there is a problem with IV cam, but I have set it up. Fingers crossed that it will work. It's my pen. As usual, I can't find my pen. Okay. If I can't find my pen, I take a new pen. Right. So, can you quickly, so you write the topic connected particles, and can you quickly just copy the diagram? Put question number 1, because you will be having this. You don't need to copy the question. And when you do these problems in the exam, also you don't have to copy the diagram, but I'm just copying the diagram into my paper. It's a new topic. Friction is over, it's a new topic. New main topic, yes, it's a new main topic. You can see that the two particles are leveled in the same level. A and B. Distances. They are held 0.5 meters above the ground. Now, I still didn't even read the question. I'm just looking at the diagram and I get everything that I need to know. Okay. Then you can spend the minimum amount of time to quickly sweep through the body of the question. So two particles A and B of masses 0.4 kg and 0.2 kg respectively are connected by a light inextensible string which passes over a fixed smooth pulley. The pulley is also smooth, no forces there, no friction there. We don't have to worry about anything that is happening outside of the two particles. Just focus on the two particles. Both A and B are 0.5 above the ground. This is where okay, and the particles hang vertically up to there. It's all given in the diagram. We didn't have to read that. It's given in the diagram. All that information can be absorbed just by looking at the diagram. They have just repeated it. Okay, it starts. What you have to know starts now. The particles are released from rest. Very important. They are released from rest. If you have to later apply some equations of motion, both of their initial velocities are zero. Keep that in mind. But we are not going to be needing that right away. Then in the subsequent motion, B does not reach the pulley. So you can see A is the heavier one. So A will start to come down, B will start to go up. They are connected, so they will have the same. What would be the motion? What's the motion? Would they go at a constant speed or accelerate?
Accelerate.
Accelerate. They will accelerate because there will be a resultant force. If you think of each of the particles, you will see the weight and tension. We will see how that acts out. There is an unbalanced force. If it is balanced, they will not start to move in the first place, right? They start to move because there is an unbalanced force. And then there is an unbalanced force means the motion is acceleration. So the same acceleration with which A comes down, B will go up. Give me a moment, something is burning. Right? So particles are released from rest, and then B does not reach the pulley. So B is going up, A is coming down. They say in the subsequent motion, B does not, no, Mali, don't worry, the house is not on fire. The B does not, but I still get the, Amma, පිච්චෙන සුවඳක් එනවා. පිච්චෙන සුවඳක් එනවා. Burning smell. In that motion, B doesn't reach the pulley. That means, what can I say about that distance? It must be greater than 0.5 meters. Before B reaches the pulley, A will go and hit the ground. That's what they're saying. You understand that? Mali, what you are saying? Yeah, do you not speak Sinhala? Oh yeah, so it's a pichana suwadak. Okay. Do you say pichana ganak? Okay.
Yeah, because it smells.
It's a smell. Yeah, it's a smell. Smell has no positivity, negativity. It's not a good smell, bad smell. It's just a smell. A smell is something that you feel to the nose. Ganda or suvanda.
Oh no, because I find gas kind of bad. Not kind of bad. It's bad. It's strong to your nose. So
It's just a burning smell. It's a burning smell. Hello, come back to the lesson, come back to the problem, okay? So I hope it is clear to you why they say that that in the subsequent motion, B does not reach the pulley, why it is important for us to know. So that length is greater than 1.5. And A remains at rest after reaching the ground. So just for a moment, visualize what will happen here. You release it from rest, A comes down, B goes up, right? B hits the floor sorry, A hits the floor before B reaches the pulley. A hits the floor, and you think about what will happen after that. So we will think about that later. We will worry about that later. For the first part of the motion, all that we have to know is that they accelerate like that. Okay. Now, part one, for the motion before A reaches the ground, just like I said, we don't have to worry about that right away. For the motion before A reaches the ground, show that the magnitude of the acceleration of each particle is this, and find the tension in the string. Now, this is a common question that they start off with. You have to find the acceleration with which these particles start to move and the tension associated with this string. It would be the same tension because it's the same string that is attached to both of them, right? So the first step, I have given it in the short note, the first step in solving any connected particle problem is, number one, first step, you draw free body force diagrams to the particles separately. You draw a free body force diagram for A, you draw a free body force diagram for B, marking all the forces acting on them. And then, shall we do that first? I will share the screen. Ivy Cam. I hope. It's okay. Okay, that's just the diagram of the question. So here you are starting the answer. I will say answer or solution. Let us say solution. That sounds better. Solution. We are solving this problem now. Solution. What do we do? Side by side if possible. That's always nice to do things parallel, the work. Here's my A. I'm drawing a free body force diagram for A. Here's my A. Here's my B. I take a different color. I usually mark forces in red. Where is my red pen? Good question. I have it. Don't worry, I have it. Okay. So let's mark the forces acting on A first. Weight. How much? How much is the weight? 4 Newton. 4, correct?
Yes.
Okay, and then tension upwards. It's hanging. It's hanging by the string. The string is pulling it up. Tension. Do we know how much it is? No, we don't. So you mark it as T. Are there any forces acting? That's right. No. Good. And then you have to mark the direction of the acceleration with an arrow alongside the object. So not on it, not the way you marked forces, but alongside of it. Like here, it's moving down. To indicate acceleration, put double arrows. Do we know the acceleration? We don't. Just write it as A. That's your complete free body force diagram for A. Then for B. For B, weight of B, how much?
2 newtons.
2 newtons, very good. So also notice that I'm not putting the units in my diagrams. That we do for convenience. All values are written in their standard units. So 4 means 4 newtons, 2 means 2 newtons. This is a force of 2 newtons. And then tension, same tension. B also is hanging, tension upwards on B, same tension. But B is moving or accelerating upwards. Same A or a different A? Same A, they are moving together, same acceleration. Right? That's the first step. This should not take a lot of time. So since this is the first question, we are taking it slow, we are doing it slow. that has to be a quick step. Okay, and then the next step, this is not even a step, that is a step. Okay, let's consider it a step. The next step is to apply F equals ma. If something is accelerating, what can you apply? F equals ma. Connecting the forces and the acceleration. F equals ma. That's the Newton's second law, is the law or the formula, that relates all the forces to give you the new net force, capital F, and the acceleration. So the next step is to, after drawing the free body force diagram, you apply F equals ma to each particle in the direction of motion. Remember, F equals ma is a vector equation, which means it has to be applied in a certain direction. In what direction do we apply it? In the direction
Down.
of motion.
Yeah.
Motion. For A, so I will write underneath it. If you are not doing it like this, you have to say, when you apply F equals ma, you have to say to which particle you are applying it. Now, the way I am presenting my work, I don't have to say it, because under A, I am doing the work for A. Under B, I'm doing the work for B. If you're not doing it like that, then you have to say for A, like this. I will write it here just for you to know. You have to say for A, for which particle you are applying that equation. For A, downwards, you apply F equals ma. I didn't have to say this because I'm writing it underneath A. Let's apply F equals ma to A. What is the net force? It's accelerating down, obviously, because 4 is greater than t. So it's 4 minus t is the resultant force. Two forces, the resultant force is the bigger force minus the small force, and the direction of this force is downwards, right? Is equal to mass times acceleration. There I have one equation. I have two unknowns here. A and T are unknowns. So as you can see or predict now, oh, Dimandi. Oh, that's okay, Bimandi. I'm glad that you were able to join, and thank you for letting me know. We are just starting the first question of connected particles. I have sent you the note and the questions. Okay, just try to follow from this point onwards. We just started it. You didn't miss much. We'll see. I will send you the recording as well. Okay, so I have now one equation here connecting A and T. Let me label it as 1. And if you remember the first question that we had in this question, let me take you to the question again for a moment. What do we need to find? Show that the magnitude of the acceleration, that's A, and find the tension, that's T. So we are supposed to find those two unknowns. And I hope you can see now that if I apply F equals ma to the other particle B, I can obtain another equation involving A and T, and then maybe I can solve the two simultaneously and find them. This is what happens in every connected particles question, right? So now go to B, you keep this as it is, this first equation, go to B and apply. I will write for B, I don't have to, but I'm just writing it anyway. For B, you apply F equals ma upwards, because it's moving up. T is greater than 2. So it's T minus 2 is equal to 0.2 is the mass A. That's number 2. Now, you simply solve these two and find A and T. Let's add. That work I will do in the middle. 1 plus 2. T gets cancelled if I add. 2 equals 0.6A. Therefore, A is equal to, how much do you get? Do you get that? This is part 1. please put part 1. I forgot to put the part number. Did you get that? Now, can you substitute that into either 1 or 2 and find T? What do you get for T? That's correct, Hatfi. 8/3 newtons. Put the units in your answers. Nowhere else you have to worry about units as long as you are using standard units. And finally, in the answer only you can. What does it mean when string is taut? Means it's not slack. Opposite of slack is taut. So when you are hanging something in a string, it's taut. You get that? Right. So for example, in the beginning of this system, let me go back to now. I hope everyone got these two answers. If I go back to the question, in the beginning, this string is taut. And then while it is moving, the string is taut. If the string is not taut, you can't have a tension acting along it. When you pull it, when you pull a string, when it becomes taut, only there is a force acting on it. When it is slack, there is no force transmitted through it. Can you feel that? Take like a wire or a thread. Like I can keep a thread slack in between. That means there is no force along it. But if I pull it, when it is taut, then there is tension in it. You get that?
Yep.
Right? Okay, then, oops. So part 1 is done. Let's look at part 2. Part 2, find the maximum height of B above the ground. Now, this part needs some analysis, some thinking, some slowing down and contemplating and really thinking what happens to this system after A hits the ground. Okay, so this is a part of connected particles problem that you get. I have explained it in the I will take you to the wait, I will just share the, give me a moment, I will open the before I should, don't look at it, stop share. I want you to think, okay? I can just tell you when this happens, that happens. Can you think about this? It's nice if I can show you actually two things, like we could have done it like an experiment. Can you explain to me what happens? Okay, now this is going up, this is coming down. Say at this moment, this A has hit the ground, hits the ground. After A hits the ground, we will assume that it stays still. We'll assume. It might bounce back, we don't care. It stays still. What happens to B? Let's assume, I'll repeat that again. Let's assume after A hits the ground, it comes to a rest. What happens to B? What's the motion of B that point onwards? Oh, really? You think it'll, like that it'll stop? No. Just think of a real scenario. Now, this might bounce in a real scenario. Or if the, depending on the depending on the type of surface that it is hitting on, it can bounce or it can actually like stop immediately. That can happen. Assuming that A stops, at that point onwards, what's the motion of B? Does it stop too like that in right there? So that, yes, Kavindi, very nice. Kavindi, say it to everyone. Kavindi says it will still go up to some extent. Imagine this happening. It's like, oh, that sound. Do you hear it?
Slightly.
Slightly, no? It's not the neighboring house, it's the house after that. So I have no way of even. No, it's not Pirit. They're mowing the lawn. I think. Neighbor. That's right, Mihir. Malit, how are you? Have you? Let me. Yeah, right. Let me wait. Let me check that. Have you renamed your profile name with the word host, or are you actually? Oh no! How come you are a host? You have renamed it. Oh my God! Everyone, look! Check out the participants list.
I know, I noticed that.
Very nice, Walid. Savage. Yeah. It's not savage, it's just funny. No, it's not thug life, it's just funny. He has renamed his name to Malit Host. So that when some. Okay. Can you explain to me what happens to B?
Miss, it will go up. Okay, now as Kavindi said, it will move up and at least then it will come to rest, right? Or no?
Right? Yes. Then it will come to rest and will stay there at rest.
Yeah.
Floating.
After everything, it will stay at rest. Or it would come again down.
So now you have to really imagine this. Shall I draw it? Now,
You draw in the whiteboard.
there,
No, the other.
the actual
The
one,
virtual one.
virtual. You all do it. Oh, I can do it in the. I can draw it in the. Yeah, let me draw something on this. We didn't use this in a while. No?
Miss, isn't the IV cam working anymore?
It is working. Do you want me to draw there?
Yeah,
Yes, miss.
it's
That's
it's
also okay.
clear, much clear
It's
there.
much more realistic.
Realistic. Okay. Realistic. I will become realistic. I will be realistic. Okay, so let me just keep this here. Here's your realistic board. Okay, so here's the first. Okay, I will draw step by step. Okay, stage one. Stage one. That's the cup here. That's a pulley. That's A, and that's B, and here's the ground. Is it too small?
It's okay.
No? Right? Here's the beginning. T equals 0. Beginning, start. Okay. Then so I'm going to like progressively draw different stages of it. Then this will start coming down. Say when it is somewhere here, this will be somewhere here, right? So this is going down, acceleration, this is going up, acceleration. Here's the ground. It's very close to the ground. Here's the point. Here's the point. Here's the point. It hits the ground. Okay? Okay? A hits the ground. what happens right after? Up to this point, if you think of the string, it's taut. The tension is there, acting. Tension is there. Here T is there. Here T is there. At this moment, T is still there. And T is about to get, you tell me what, right, next millisecond. Remember, this last moment, A was moving up, isn't it? A and B both, sorry, not this B, I'm sorry, I hate that when that happens to me. I swear, when I want to say B, I say A. When I want to say left, I say right. I don't know why that happens. A and B, let me write A and B, okay? Did someone say something? Ah, you have said so many things. Wait, I can't see the chat. Why can't I see the chat? Oh, okay. Miss, there was another power cut just now. Oh, wait, IV complete. So how can I go down again? What? String is inextensible. Yeah, the length of this string is the same. Like if it is 5 meters long, it's 5 meters long everywhere. What do you mean? So how can it go down? What do you mean? Oh, it's going over the pulley. It's moving. Ah, you thought it's stretching. This is not stretching. That's a good question. Did anyone think that what happens here is no, how can that happen? The string is moving with the particles. Malit, is that clear? Ah, okay. Good, Nathan. Tarindu, you had another power cut just now. I'm sorry to hear that, but we are glad that you are back with us. Okay. Right. I'm discussing now. Right at this moment in time, B has that acceleration. It's like this. When you are in a bus, when you are in a bus and the bus is moving, you have the speed of the bus. I hope this is a good example.
Yes.
The bus stops suddenly. You would still have that speed. You would be moving and you will slow down and come to rest and come back. Or think of
Or we can take this as well, miss. If you're like, let's say a person is moving on a vehicle that's at 25 meters per second, and he throws a ball, that ball will remain at that same position and not move. It will fall straight down.
no.
Yes, miss. Versus that means the motion of the ball. That means the man throws the ball. It's like this.
If you are, say that again, how did you start? You and the ball, you are holding a ball, you are moving at 25 meters per second. Okay,
Okay.
When A falls, the string becomes taut, so to reach equilibrium has tighten again. I don't get what you're saying. Okay, let's take one person at a time. Nathan says yes. Yes,
Can
Malik.
so like by the time A falls down, the string is like it's not stretched exactly, right? It's kind of
It is not stretched ever. This is not a stretch.
yeah. So it's but it's loose, right?
At this point, after this point, it becomes loose.
Yeah.
After this
So
point.
then because it's loose and it has to reach equilibrium at that position, so like in the end somehow it has to be stationary, no? The two particles again, they can't keep moving like that, no? So then by the time A falls, B kind of goes down and then comes up again and then stays
B
stationary,
goes
right?
down? How can
Is
B
that
go
how it?
down?
Miss, what he meant is it moves and comes back to rest, right?
That's right, Mihir. That's right. What happens?
Yeah, that's what I was talking about.
Okay. What happens after this is next moment. Now this is hanging down. This part, B will still keep moving up. B will still keep moving up, and then the string will become slack there.
no, that's what I was talking about.
That's what you were talking.
Slack is the word.
Slack is the word. Okay. So no tension on B, no T now, but it's moving up. After this point, after this moment, let me draw a dotted line in that level. B's motion is just motion under gravity because no T anymore, only the weight. It's just like it's been thrown from that point upwards, and it'll go up, and it'll stop, and it'll come back downwards, and it'll come back downwards until it is taut again, until it is taut again, and it'll stop. You understand? So B, if I show here, oh, do you see what I'm drawing? Oh, it's not. No, you're not seeing what I'm drawing. Let's wait a moment.
Miss,
Yep.
when we take the initial position of the string, there is a tension in the string.
Here?
Yeah.
Yeah.
Is it the same as when
Yes.
the particles are moving?
Of course. Why would it change?
Okay, Miss.
Because it's the same, even in the big, it's the same for all together. If you think of all the forces acting on these particles, it's the same for forces, the two weights and the tension. They are moving under the same four forces. Tension, there's no reason for the tension to change. Okay, so the motion of B from this point, if I show you in a separate diagram, it just goes up and comes down. Okay, this is the motion of B from this point to this point. It's a little motion under gravity because no tension. During that motion of B, the string is slack. So no upward pull on B. It's just when A hits the floor, tension disappears. At this point in this picture, tension at that point in time, tension disappears. But since B was moving, now here B is moving with the same acceleration. It has the same acceleration. And when T disappears at that moment, in this diagram, I should have drawn the next moment, the same diagram, next moment. Can I insert that diagram here? No, it won't be clear. Right, before it is in a higher position, in the same position, when there is no T, it's only W, then the acceleration would become just G, gravitational acceleration. It will continue moving with gravitational acceleration, but it will be starting with the same velocity. It was moving here. The initial velocity would be the last velocity it had here, which is the velocity of A. They are moving together. No? Their velocities at any given point in time is the same. They both are moving together. So the velocity with which A hits the ground would be the velocity of B right at this moment. And for the motion under gravity for B, the starting velocity would be that velocity. Did you understand that? So let me give you a minute to just really think about that. Please take some time to think about it. Process it, please. Nathan, my previous example wasn't accurate, but I think this one will be. And he was riding a bike and he used the help of a fast car to get on ahead. Okay. How does that relate to now this example? When you're riding a bike, if you hook yourself up to another vehicle that is going faster, you're just adding an additional force. what actually happens here is, can I draw another new set of diagram? He had the more, yeah. There, no, now you're riding a bicycle, and then you can, if you hook yourself into a moving vehicle, you can stop pedaling and just wait, like you will be dragged along with the vehicle. That's something that is not what is happening here, isn't it? Wait, let me explain it to you again in a different set of diagrams. I'm just drawing B now. This is B. This is B, and there's the string. This is B when A hits the ground. This is when A hits the floor or ground. At the moment when A hits the floor, I haven't drawn the full things. It's going like that. I have just drawn B. The moment A hits the ground, still the string is taut. See, I have drawn it taut. Tension is there. And this is kind of moving at A. And it will have a certain speed at that moment. The next fraction of a second, when it is still there now, or we'll say it's just a little above, it's just a little above that position, little above that position, the string slightly start to slack. Okay, so no T disappears, no T. So the only force now, here you have weight, only force now acting on B is its weight. And B had a certain velocity here, the last velocity it had here, I'll call it U. So it's like it started with the velocity U, and now it will start moving. Now this is becoming more slack and slack, more slack. Okay, now it's more this. So what is the acceleration here? G. What is the acceleration here? G. It's going up, and it'll go up like that, become more slack, and it'll stop, and it'll start coming back down until and finally
Miss,
that.
Miss,
Yes.
my mic. Can you all hear me?
Can.
Okay. No, my mic wasn't working, so I had to try the. Miss, I understood the thing. It's just that you were talking about the bus and a person, right? Where we are on the bus and we had the motion of the bus when the bus at once stops.
Yeah.
So I was just thinking for that example. My previous example, I didn't actually quite fit in.
Yeah.
So my what I thought was, I just came to me that was this that thing, Mr. Bean. Let's just take he's a station object. He used that. He had the motion of the car when the car stopped, right, Miss, and he just jet on ahead. Like he just held onto the car. Let's just say he's a stationary object, and he was just moving with the car with the same speed. Yes.
I don't get it. He's driving the car?
No.
He's in the
Miss,
car.
He's on the bike.
He's on a bike.
He's on the bike. He grabs hold of the car, and he just goes with the car. And when the car just stops at once, he has the motion of the car.
That's right. If the
that's what I was trying to say.
That's correct. That's correct. So you're holding the car. You're just cycling, and you're holding a car.
Yeah.
Then you don't even need to pedal then, right? The tires will just rotate because the car is providing that force. It's dragging you along. And then if the car suddenly brakes and stops, you would still be moving.
Yes.
You had that. This can be explained using different notions called, I don't know whether you have heard of inertia.
Okay.
Do you do inertia in physics?
Yes, we do.
Yeah. Or just Newton's first law. As law. Do you see here there is a resultant force. The resultant force here is T minus W. In this case, the resultant F is T minus W. That's what causes this acceleration. And suddenly at this point, your resultant force becomes just W. So your acceleration changes. It's what acceleration is it now? Gravitational acceleration, because you're just moving under weight, under gravity. And then you keep moving up. Why do you keep moving up? Because you were moving up. You had a certain speed here. There is no reason for you to just stop. How for you to stop? Think of Newton's first law. For you to stop, there must not be any resultant force acting on you. There is a resultant force acting on you, W, in the opposite direction to your motion. That's why you slow down now. You're still moving that way, but there is a force pulling you behind. So you slow down and then you accelerate down again. You slow down up and then you accelerate down back. Was that too much? Or did you understand?
Understood, miss.
Understood. Others, can you just give me a quick response? Okay. Good, Hatvi, Kavindi, good. I hope it's clear to everyone else. It's worth spending a good amount of time really understanding this, because this comes up in a lot of problems. You have to know how to think about this and understand this motion. Okay, so please make sure that you understood this. Then let's now go back to that part 2. We have to now, okay, so if I go back to this, from here to here, both A and B were accelerating with a certain acceleration, which was, we found it, which was 10 divided by 3, 10 upon 3 acceleration. After that point, A doesn't move, B moves with 10 meters per second squared, different acceleration. So these are two different parts of motion of B. If you think of B, first part of motion of B was with one acceleration, 10 over 3. Next part is G. Is that clear? Two different accelerations. Right?
Understood, miss.
Understood. Okay. Now let's go back to the question. Oops, not that. Not that. This. Find the maximum height of B above the ground. Find the maximum height of B above the ground. For that, what you have to do is, what do you think we should do? So for that subsequent motion, after A has hit the ground, we have to just think of B's motion. Up to that point, up to where A hits the ground, how far has B moved up? Now think and answer that question. Up to the point A hits the ground, during that time, how far has B moved upwards? What distance B moves upwards?
0.5.
0.5, very good. A goes 0.5 down, B goes 0.5 up. And then that point onwards, B moves under gravity. It does the motion like that, goes up and comes down. It's like you threw something up, that motion. Okay. So you will have to find the maximum height of B. So it's going to be 0.5 plus, that is how far it was above the ground first, and another 0.5 up, that's how far it moved, plus that little distance it will go up under gravity. Is that clear?
Yes.
Everyone?
Yes, miss.
Yes, right? Okay. So you only have to find 0.5. It started already 0.5 above the ground. It moved another 0.5 up. So that's 0.5 plus 0.5 plus you have to find how far it goes up under gravity. So how can you find that little distance? You have to apply equations of motion to that little bit of the motion of B. Acceleration there is 10. Final speed on top is 0. You need to know, we want to find the distance you need to know initial speed. Initial speed of B. Initial speed of B for that motion would be the speed with which A hit the ground. Is that clear? Because that's the last speed B had. When A hits the ground with a certain speed, that's the same speed that B would have just before it starts to move under gravity. So that's the speed, that's the starting speed for B for the motion under gravity. Is that clear?
Yes.
Okay. So can you first find U for B? Now you need to write all that. If you let's write this. Okay, let me take you to the okay. You can, so to find that initial speed of B for the motion under gravity, you can either find, can you try finding that? You can find it by applying an equation of motion to B itself for its motion before. Like if we write or to A, they both have the same speed now. Let me show you applying for B. If I write for, now this is part 2. For B's motion, now I'm focusing on motion. So this is about equations of motion. For B's motion, how do I write it? During the string is taut. Oops. If I consider that section of motion of B, it's moving upwards. Okay. What's initial speed? So from the beginning, from this till A hits the ground, for the motion of B, what's U? We know A, we know S. We want to find V for that, because that V would be U for the rest of the motion when the string is slack. What's U? How did they start? They started at rest. You released the system from rest. So the initial speed of B for this motion when the string is taut is 0. What's A? For that motion, what's A? You need to talk.
10/3.
Good. Thank you, Tarindu. 10/3. What's S? How far did it travel? How far did it move during that time?
0.5.
0.5. Thank you, Nathan. You can find that last velocity B had when A hit the ground. You could have found the same thing by thinking of A for its motion downwards. Same thing. What's the equation? S V squared equals U squared plus 2AS. Plus 2 times. Sorry, I'm yawning. Such a bad teacher, yawning while teaching. Because I feel really tired today. I feel tired at this time anyway because it's warm. And yeah. This time is bad. It's not a good time to have a class. Middle of the day. It's the warmest time of the day. What's your answer? Huh.
10/3.
Root 10/3, isn't it?
Yes,
Yes,
root
root
10/3.
Root 10/3. Good, Mihir.
I didn't say it.
I heard your voice.
I said
Okay. Right, now that speed, this velocity would be the initial velocity for the next part of B's motion, which when the string is slack. So let's apply, let's say for B's motion, now to a different part of the motion, we are going to apply more equations of motion again. For B's motion during the string, you have to write all this. During the string is slack. Let me highlight that. It's important. Slack, not all the way it is slack. Until it reaches the highest point. That's all I need. Until, I'm not going to consider the whole motion coming down. I just need until it goes up. For the whole motion, the string is slack. So if I just say string is slack, that's not complete. During the string is slack until it reaches the highest point. So for that part, I know U, it's what we found there. I know A, I need to find S. What else do I know? I know V. Can you write what those are? S is what I'm interested in finding. What's U? Mihir, what is U?
Miss, U is root 10/3, right?
yeah, that's the.
Yeah.
What's A? Mihir. I want from Mihir.
Okay.
That's 10/3, right? Similar.
A. When the string is slack, with what acceleration is it moving now? It's moving under gravity.
10.
And now don't jump and say the answer. Can Rachel?
Sorry.
Excuse me, miss.
Oh, fine. Yes, who is that?
Miss,
Khalid, yes,
so
fine.
the string is slack, right?
Now it's
At
slack.
that, yeah, at that moment it's slack, right? So doesn't it mean that A is still pulling the particle?
A is not pulling the particle.
No,
It's slack.
yeah, so it becomes slack because of A's movement, right?
Because A has hit the ground.
Yeah, so still won't that acceleration 10/3 be applied?
How? 10
Miss.
Okay. No. Now I got it.
Okay.
Since A is in rest, that acceleration isn't there anymore, right?
No, yes. It has stopped down.
Okay.
And that tension is not there. That's why A has changed. That's why acceleration has changed. 10/3 was caused when when the particles were under two forces, tension and weight. Now tension is gone. It's only weight. With what motion does a particle move vertically? Only under its own weight force. Gravity. Yes. Rachel, can you tell me what V is here? I'm just trying to get you all to talk. Only Mihir, Nathan, mainly Nathan and Malik, and sometimes Mihil and Tarindu are the ones who interact. Rachel, what's V here? Anyone else? Okay, anyone else? Can you tell me what? And Kavindi also dropped message.
Me?
No.
Can I say?
No.
Okay.
What is V here? Mihil, you're right. Mihil, you're right. Somebody else. Thank you, Umalia. Yes, 0. Because we are considering on up to the highest point. Okay.
Miss, is it
Yes.
because it's going to rest?
Because we are considering up to the highest, because we are considering until it reaches the highest point.
Yeah.
Goes up and comes down like that. We are only considering this part of the motion. It will go up and come down. We are only considering up to that highest point. This is B. Ooh. That's all. Okay. Can you find it then? Can you find S? Same equation, no? Hurry up. Is it 10 or minus 10? You are applying it upward.
Minus.
Minus 10.
Can I tell the answer?
Yeah.
106 meters.
Therefore, now we are ready to answer the question. What was the question? Find the maximum.
And the maximum height.
Therefore, maximum height of P is 0.5. Oops. Plus 0.5 plus 1/6. Half plus half plus 1/6. That is that right?
Yes.
Very good. Okay. Take a deep breath. I need that. More than you, I need that.
Miss, isn't it much more easy to just write 7/6?
Yeah.
Okay.
Fine. 7/6. Let's look at the second question. Okay. How did you feel about this question?
Good.
Good, right? Okay. Here's the next question. Can you first copy the diagram to your book? I will do the same. Number 2. So there's a pulley at the top of the ramp. Pulley. And then the string is going over the pulley. One particle is hanging down like that. This is here. Other particle is on the slope. P and Q. This is alpha. Just draw the diagram. And just like in the previous question, lot of like half of the question can be absorbed just by looking at the diagram. So if you read the question now, the body of the question, the first few sentences would cover things that you have already absorbed by looking at the diagram. Let's quickly read it. Two particles P and Q of masses this and this respectively are attached to the ends of a light inextensible string. Notice that in every question you will see that. The string passes over a fixed smooth pulley. You will see that too in every question, which is attached to the edge of a rough plane. This plane is rough. There is friction. The coefficient of friction between, let us note that down on the side, mu is 0.5. The plane is inclined alpha to the horizontal, tan alpha, let us note that down on the side. Tan alpha is 3/4. Immediately you draw up a little right angle triangle. I hope you remember this. I'm going to take you to this. They have given tan alpha. You don't find alpha using tan inverse here. You don't do that. You are going to be needing sine alpha and cos alpha when you resolve the forces. You find that using a right angle triangle. If tan alpha is 3/4, that means this is 3, this is 4, opposite over adjacent, then hypotenuse would be 5. Which means cos alpha, let's write that and keep readily available for us. Cos would be 4/5. Sine alpha would be 3/5. All that is on the side. Okay. Back to the question. Did anyone say anything? Did I missed what? Oh wait, am I saying something now?
Miss, the one we drew earlier, the one you drew in the paper, that's in the third step. It's the same thing, right?
Here?
Hello?
Yes, please.
Miss, the one you drew earlier, that thing, it's similar to the step 3 in the tute, right?
In the, you mean,
Hello?
yeah, yes. Tute means the short note.
Yeah.
Yes. Good, are you looking at that? Nice. Yes, Mihir. Okay, then what do we have? Particle P lies on a plane and particle Q hangs vertically. We know that string between P and the pulley is parallel to the line and the greater slope of the plane. We can see that a force of magnitude X acting directly down the plane is applied to P. Shall we mark it in our diagram? Okay. I added that to my diagram like that. Okay. Now, what I have given you in that short note as a strategy is, regardless of what they're asking, always start by drawing free body force diagrams for the two particles and then applying F equals ma. Because now this system is going to move. Especially if you are applying a force here, this is going to move like that. P is going to come down, Q is going to go up. Okay. Let's see what they're asking. In part 1. Show that the greatest value of X for which P remains stationary is 6.2. Okay. They're asking the greatest value of X for which P remains stationary. Can I let you think about that? Right, okay. Now, tell me, if this force X is not there, if you release this system as it is, what would happen? This system. just as given in the diagram, just with that, without the x force, what would happen to this system? What would happen to the two particles? Hurry up. Look at their masses. You should know what, you should be able to tell me. Hello.
Mrs.
we are
Everything
missing.
is in Malik. Everything is in the messages.
Oh, I'm sorry. I am sorry. Q goes down without excuse. Goes down. Sorry, Hatri, yes. No idea. I don't know how I missed that. Okay. Q goes down because Q is heavier. As it is, it's going to move like that. So if you want to keep things still, if you want to keep still keep things stationary, you need to pull P downwards. So that's what they are saying. You are applying the force X downwards in order to keep it down, so keep it not moving. So show that the greatest value of X for which P remains stationary is 6.2. Remember, so that this is related to friction. So you're applying an external force to keep P stationary. So there will be a minimum force that you can apply. There will be a maximum force that you can apply. You just have to figure out for the greatest value in what direction must friction act. That's it. Part 1. Can you draw a diagram for part 1? Only draw forces acting on P. We want the greatest value. We want the greatest value. Oh, this is stuck. Okay. Here's P on the slope. I'm just drawing P. Here are the forces. You have here's X. Here's R. Here's tension from the string. The weight I will split. Shall I split weight? This is weight. I will draw that in black. Components of weight. What was the mass of P? 0.4. I don't see the chat sometimes. So force on Q should be equal to force on P. No, what do you mean force on Q should be equal to force on P? Which force are you talking about? You can't just say force. So many different forces are in play here. Weight, tension, reaction, friction. Which force acting on which one? So this would be 4. So this is alpha, 4 cos alpha. This would be 4 sin alpha. That's the weight, components of weight. Now friction you have to put in what direction? If you want the maximum X, na? I'm so absent-minded. Is it maximum X? Greatest X. For greatest X, in what direction must up the slope? Very good, Hatri. Here's F max. Now this is the key in this question. Placement of F max. Knowing in what direction friction has to be added to the diagram, depending on what they're asking. They are asking us the maximum value of X. Okay, so let us write on top here for maximum X. This is how forces would act. All these would be the same. It's just maximum friction, that would be different. If we want the smallest x, F max would be in the same direction as x. So I hope you remember all that. We have spent enough time talking about that thing. Okay. Now we want to find this is the maximum x. So this would be max x max. Shall I write x max here? So it's at rest. You consider conditions for equilibrium. So it's in equilibrium. If you think of equilibrium this way, that's vertical equilibrium. R must equal 4 cos alpha. R must equal 4 times 4 over 5. That is 16 over 5. Oh, I'm sorry, you can't see what I'm writing. What am I doing? Okay. Then horizontal equilibrium. So I will put this like that. Then horizontal equilibrium, they are balanced. X max plus 4 sine alpha must equal T plus F max. How do we find T? How do we find T? To find T, who can tell me? Let's go back to the original diagram. Remember, T is a common force that acts to both P and Q. Same string, same tension to both of them. Very good, Malit. Take Q. Quickly consider, shall I do it on the side here on a little bubble? I'm going to do it in a little bubble here, in a little bubble here. I'm drawing a free body force diagram for Q. This is Q. It has only 2 forces, tension upwards, and what's the weight of Q? 0.7. So it's 7. This is 7. Okay. There is no F equals ma. It's not accelerating. It's in equilibrium. Here, vertical equilibrium, when you consider vertical equilibrium, T is equal to 7. Done. You found T already. Just by thinking of forces acting on Q, I can use it now here. X max is what I want to find. X max is what I want to find. Plus 4 times sine alpha. I have sine alpha there. 3 over 5. See how everything comes together. T I found 7. What is F max is mu R. Mu R. Mu is given 0.5. R I found here. This is mu R. This is mu R. Okay. If anyone can't remember that. Therefore, F max. You find it now. And I will leave that for you to complete. Okay. Shall I change the screen? Again, you have said things and I don't see the, oh, you already got the answer. Answer is 6.2. Yes, Malit is correct too. Malit and Hafi, very good. X max is 6.2. Okay. Part 2. Can I let you try it for homework? Part 2. And I will not give you any homework. I'm not going to leave you because we need to discuss and do a couple of questions until you get the hang of it. And then I will let you do on your own. But since we are in the middle of this question, I will let you try part 2. Not compulsory, just try. If you can't handle it, just leave it. We didn't practice enough. Okay. So don't worry if you can't do it. Right, so I'm just leaving part 2 just for you to try. Friction number 10, we will take up. Oh no, we discussed it, nah? Like we discussed the answer. Okay, we will continue this next time. Take printouts of the 2 documents I sent, the short note and this worksheet, and have it ready next week.